Firstly, thanks for the organizers for this very interesting conference. I've been wanted to get connected to the plasma physics community for a while. Hopefully the observation results I'm going to introduce in this talk will interest you. So I'm also going to talk about the cosmic ray sources at a lower energy in the PeV energy range, and mostly about their source natures. Now, first I'm going to have a brief introduction on the PeVatrons, and then I'm going to talk about, firstly, the PeVatron at the center of the Milky Way galaxy and the relevant observational evidence. And my last topic would be for the PeVatrons outside of the galaxy center, somewhere else within the Milky Way galaxy. So I don't need to spend much time on this because Roger has already talked about it. So the EEV cosmic rays are like to the ankle of the cosmic ray spectrum, but in this talk we are going to focus on the sources that can accelerate protons or electrons up to a few PeV and maybe even a little bit higher. That is around at least the first knee of the cosmic ray spectrum. So the biggest question we want to answer would be where and how are these cosmic ray PeV cosmic rays accelerated? What type of galactic sources can account for this population of cosmic ray particles? So even a few years ago, that was not really a possibility and has not drawn enough attention yet. But there are very rapid discoveries and breakthroughs in the past 2 years. Now in 2023, and I'm sure some of the colleagues saw this, the S-Cube collaboration basically detected neutrino signals along the galactic plane as a big blurred blob at 4.5 sigma. That might seem sad for astronomers, but it is something for neutrino detectors. That basically confirms the existence of hadronic PeVatrons within our galaxy, most likely distributed along the galactic plane. Now, another very exciting results from the TeV gamma ray community is that the LASO ground-based TeV observatory, that is in China, they released their first catalog of the UHE ultra-high energy sources in the same year, basically 2023, including about 43 sources detected above 100 TeV, so making them very likely individual PeVatron sources. So ever since, many colleagues, including myself, have been pursuing this catalog of sources and try to identify them. About 1/3 are basically completely unknown. So all these discoveries basically obviously shifted the focus from do PeVatrons exist in our galaxy to basically what are they? Now, can we identify them as individual sources? So this is a new possibility. I want to say a little bit more about our current best knowledge about what galactic PeVatrons could be. So traditionally, the TeV sources are categorized into leptonic sources or hadronic sources. So in a leptonic, including these PeVatron candidates. So the scenario would be in a leptonic PeVatron, the TeV emission come from inverse Compton scattering of the CMB photons by relativistic electrons and positrons. And it's widely accepted that relativistic electrons and positrons are basically accelerated by positive nebula, and that are basically a expanding bubble of relativistic electrons and positrons with constant energy injection from the central pulsar. And on contrast, for a hadronic PeVatron, so the protons, after they are accelerated from the primary accelerator, they would diffuse out and interact with the ambient interstellar medium. And that's where the proton-proton or proton-gamma interaction are considered to happen, producing the copious pion showers that eventually decay into the neutrinos or the gamma ray photons that we can detect. And the black hole systems, associated with different mass scales of black holes, are worth their own class as potential PeVatron candidates. They could be X-ray binaries, microquasars, and of course also the supermassive black hole at the center of the galaxy. So there are many different groups pursue for example S-Cube neutrino data to probe all these different types of black holes. It's likely like black holes are hybrid, including both leptonic and hadronic processes. Now, the already the older wisdom is like, okay, the leptonic PeVatrons, the prototypical leptonic PeVatrons are most likely parts of nebulae, for example, the Crab Nebula. That is also one source detected by lasts well above 100 TeV. Another case is a source called the Io Pulsar Nebula, studied by a group at Columbia. So they combine like multi-wavelength observations, especially the X-ray observation from X1 Newton helps a lot. They applied an evolutionary pulsar wind nebula model to the broadband like spectrum energy distribution and determined the required magnetic field is about 1 microgauss, and then the required energy of electrons needs to go to about 2 PeV. So basically, establish the Io Pulsar wind nebula as another leptonic PeVatron. However, so this older picture is being actively challenged, both experimentally and also theoretically right now, because the LASSO collaboration has indicated that for the Crab Nebula, which used to be thought as a purely leptonic, right, perfectly fit by a synchrotron emission and inverse compton scattering all the way to the highest energy, but there is right now indication on a hadronic component at the highest energy. And there could be like a detection of PeV photons there that would require like multi-PeV protons, likely hadrons, in order to explain that. And also just searching for the literature, the theories are still very, very limited, but I just found this paper that invoked a possible theory for explanation of multi-PeV protons from pulsar wind nebula like the Crab that basically invokes a re-acceleration mechanism, firstly accelerated by supernova shocks and then got re-accelerated by pulsar wind nebula termination shocks. But we definitely need like more models to help us understand what is going on. But by this end, I no longer believe we can still like very naively categorize these sources into leptonic or hadronic. It's more likely like both mechanisms contribute to a single source. It might be just a question of which mechanism dominates at which energy band. Despite maybe thinking like maybe most of the sources are hadronic, including both leptonic and hadronic sources, but still observationally it's challenging to confirm like which source is hadronic. So the smoking gun that we would really want to see is, of course, detection of neutrino, right? That would be undeniable evidence for hadronic processes. But some of the like leading candidates for like maybe hadronic dominated PeVatrons are the Galactic center PeVatron, and that is likely associated with the supermassive black hole Sagittarius star that I'm going to talk more about. And another case has drawn a lot of attention in the like TeV community, also neutrino astronomy community, is the Boomerang Nebula. That is a very complex region, including both a supernova remnant and also a pulsar. So that could also have a strong hadronic component. So next, I'm going to firstly talk about the PeVatron in the Galactic center before I talk more about other PeVatrons elsewhere. You've already seen this picture, I think, in one of the slides Roger talked about. So there has been a strong observational evidence that there is a hadronic PeVatron at the very center of the galaxy, located within about 10 parsec of the dynamic center of the Milky Way, with Sagittarius star, the supermassive black hole, as a very likely candidate. So the strongest evidence comes from the Hess result about a decade ago. That shows that the TeV emission spatially correlates very well with the molecular clouds, and that is a strong indication for the proton-proton processes. Right? The scenario would be PeV protons come from the very center and shoots towards all the directions. When they interact with the molecular clouds, they would produce like pions that decay into neutrinos and also TeV photons that we are seeing here. So the question would be, is the supermassive black hole the the candidate, or should we consider other possibilities, right? Like maybe stellar clusters or supernova remnant, because the Galactic center has everything there. So maybe we can just pause a moment and think about, okay, so there is a hadronic PeVatron in the Galactic center. So what are the observational effects, possible observational effects, right? So the proton-proton interaction would be very messy, producing all sorts of secondary particles, now including like maybe hundreds of TeV neutrinos. So theoretically, that can be detected by even the current neutrino detectors like IceCube. So like Kavli has a graduate student who is working on the inner like a few tens of parsec of a galaxy using the IceCube data. On the other hand, has already detected this component, right, where the neutral pions decay into gamma ray telescope, already observed. So this is a check, this is being explored. On the other hand, the secondary particles would also include multi-hundred TeV electrons inevitably, right, in company with these populations. So if you put like the hundreds of TeV electrons in the galactic center magnetic field on roughly on the order of like 10 microgauss, you would expect to detect X-ray emission from them. However, you have to be very careful of choosing what type of sources can help you to indirectly probe 100 TeV electrons in the galactic center. So that I would connect this population of secondary particles from these hadronic processes to an interesting phenomenon in the galactic center, and also pretty unique. So that is the galactic center filaments, already discussed yesterday in one of the theoretical talk, right? So the filaments is not a new thing. They were discovered in the, I think, 1980s by Mark Morris and Farhad Yousafzadeh, firstly using the radio telescopes. So this is the galactic center, about 100 by 300 parsec. Horizontal is the galactic plane. Supermassive black hole is something, the Sagittarius is here. But I want to draw your attention to these structures, right, these filaments. So they are very well known, and also the Meerkat radio telescope has detected about 150 of them. So they are like they extend up to like a few tenths of parsec. So very, very thin and long, some with a curvature, some does not. And they are as thin as like a 1 parsec. So there have been like a detection of radio polarization, basically confirming the synchrotron emission. The magnetic field within the filament is considered to be about 100 to 400 microgauss. Again, 1 order of magnitude higher than the surroundings, making them very nice structure for us to study relativistic electrons, right? And the magnetic field lines are sort of accepted to basically distribute it along the filaments. Now, in order to produce synchrotron radio emission, then we need to feed the filaments with the GeV electrons. So we are not in short of like GeV electron sources in the galactic center. Many sources can do so. So very likely just from direct particle acceleration. But at the same time, let's not forget that in the X-ray band, we've also seen many filaments, but at smaller spatial scales. Right? Like Chandra, XMM Newton, NuSTAR have all detected filaments in the X-ray band. So in the literature, you can find about between 20 to 25. Some have the radio counterpart, some do not. Now, polarization, of course, haven't been detected yet. But if we believe like synchrotron goes from radio all the way to synchrotron, that indeed would require about 100 TeV electrons. Now, direct acceleration would be more unimaginable. So I wonder whether that could be indeed like a secondary products from these hadronic processes, especially considering some of the X-ray filaments are spatially coinciding with molecular clouds. Okay, I want to show you more like cases of the observations of the filaments. So this is a filament we studied a long time ago. So here's the data from Mark Morris, the radio observation. So this filament is called Sagittarius E. It's located at about like 10 parsec from Sagittarius star. So you can even see the fine structure of seemingly entangled magnetic field lines within the filament. So that is like amusingly similar to, I think, one colleague shows what GPT-5 thinks what the relativistic, like astrophysical, like a turbulent plasma would look like, but this is real data. In X-ray, we also detect this filament all the way to 50 keV, straight power law. And if we just naively look at the power law index in radio and the X-ray band, that's still consistent with a synchrotron. So up to 50 keV detected by new star, no cutoff, no energy break, basically. So if we consider the most likely range of magnetic field within this particular filament, that indeed requires 100 to 200 TeV cosmic electrons. So these electrons would cool off very fast, right, in the galactic center. On the other hand, these filaments have shown no obvious variations in either radio or X-ray emission on the time span of tens of years, right? For like about 50 years of no variation in radio and at least more than 25 years of no variation in X-rays. So needs some mechanism for the injection of new fresh electrons. But another case, this might be a different story. So this is another case that we studied in recent years, also a filament in the Sagittarius complex, about 30 parsec from Sagittarius star. So in this case, you can see this is X-ray data, like the Chandra observations. It's also very thin and long with a light curvature, but what makes this story different for this filament is that we do see a point source in the middle. So it's more likely like this is maybe the involve like a direct local particle acceleration mechanism rather than some like from some secondary electrons from outside. So the story is complicated. Yeah. So we have some like ongoing efforts. So I have a new student who wants to pick it up again. So this is a topic I keep revisiting in the past decade because they are so peculiar and very, very unique structures. So in the X-ray band, we are using the deep like Chandra observations, just focusing on the central a few tens of parsec of the galaxy, and we are seeing even more filaments. I think our hope is that we can basically double the number of known X-ray filaments as reported in the literature right now. That should give us a very good position to do a systematic correlation study between the X-ray filaments and the radio filaments. There are 150 of them, and maybe we will have about like 40 to 50 of the X-ray filaments. So what we want to deliver maybe to the community would be like a catalog of these filaments by combining both radio and X-ray data. Now, I also want to draw your attention to this filament. It is pretty interesting that my student is studying. So the image itself in red, yellow, white is the Meerkat radio data. It is very thin and long. It's a rare filament. It's like perfectly like linear without any curvature. While in X-rays, we can detect it up to 20 keV. Like spatially associated with the radio filament perfectly. So the X-ray data is represented by the green contours there. So this is pretty interesting. We seem to see both thermal and non-thermal emission from these filaments. So what kind of mechanism we can use to explain these filaments? Right? There can be a global mechanism, right? Maybe from like a secondary electrons, and also it could be like some like lower energy electrons could be driven by a outflow from Sagittarius star or other galactic center sources, feeding maybe GeV electrons to these filaments. Because the Meerkat also show two components of these filaments. The first population are associated with the bipolar radio bubbles, right? They could be driven by some wind from the galactic center. And another population is concentrated like this along the galactic plane, possibly like correlated with the molecular clouds. Now, I tend to would focus more on this population to think about the connection between the filaments to the secondary multi-hundred TeV electrons from the hadronic processes. So here is the model in my mind by connecting these filaments to to the galactic center PeVatron, like we have this accelerator, like proton accelerator in the galactic center, and they could like accelerate the protons into the PeV energy, and once they collide into abundant molecular clouds, right, in the galactic plane, and they would produce secondary electrons up to a few hundred TeV, right? And some of them, if they escape from the molecular cloud and somehow got injected into the filaments, that could explain what, at least a portion of the filaments that we are seeing here. But so far, it's just an idea. We need very careful treatment to test this, including the cosmic ray like diffusion in the galactic center magnetic field and all sorts of detailed things. So we just started to do very simple like simulations to see whether it can work out. So I'll put it like this. So I should have 10 minutes or so that I want to introduce our ongoing efforts in identify other PeVatrons outside of the galaxy, mostly based on the LASSO source catalog. So as I mentioned in introduction, so in the LASSO source catalog, about 1/3 of them are unidentified. So they only have like LASSO detection with no known lower energy counterpart, making it almost impossible to identify their source nature. So what we are doing with several groups in US is like we are pursuing new observational data in lower energy, like to try to understand, like, okay, no detection in lower counterparts, is it due to simply due to like a poorly explored, or is it like a truly nothing in lower energy? Maybe that would suggest the PeVatron is a transient PeVatron that used to be efficient, right, in accelerating particles, but no longer so, just leaving the TeV emission there only. So as the first trial, we pursued the XMM X-ray observations for 4 out of the unknown LASSO PeVatrons. And I'm going to show you these results. Most of them are published within the last few months. So let's look at this case, telephone number name. So this source is detected by LASSO above 100 TeV at a high detection significance. So previously there's no known like a low energy counterparts except for unidentified Fermi sources. So there's a theoretical paper out there last year tried to interpret it as a molecular cloud illuminated by a supernova remnant somewhere. So in our like X-ray, like the XMM Newton observation, so this is the entire field of view of the XMM telescope. The size is comparable to the LASSO source size, considering both source extension and the position uncertainty. But basically, we are looking at nothing. There's no X-ray source. Instead, we can establish an upper limit in X-rays. But the upper limit alone can help to put a tight constraint on the magnetic field at below 1.5 microgauss. So we combined the X-ray results with the Hawk and the Veritas results and published it very recently. In another case, we got lucky. So this is another source also included in the first catalog. So this source detected up to 200 TeV as a slightly extended source. Also, the same similar story. No previously known low energy counterpart before. But here's our like XMM results, roughly in 2 to 10 keV. And this time we do see something. Now again, these white circles are basically the LASSO source positions. But this time in X-rays, we see one extended source, we consider as a primary source, plus a dozen point sources. Most of them are not in any catalog. It's the first time X-ray observation of this sky area. Now, of course, our got like immediately like interested in this source and do a careful analysis. So both the spectral and morphological data pointed to be most likely a pulsar wind nebula. So we think the story is that this is probably another pulsar wind nebula driven PeVatron. So So my postdoc, Steve D. Kirby, led this analysis. So he also tried, so right now I think we cannot rule out any, when we do the spectral energy modeling, we cannot rule out any possibility. So we tried both leptonic and the hadronic. So it's almost impossible to really rule out a hadronic model. We presented the leptonic model, like synchrotron inverse Compton scattering, only because the hadronic model needs too much assumption. Many parameters are very poorly constrained by observation. It's not like a simple and clean. So the purely leptonic model can still work out. But again, really hadronic model cannot be ruled out. Like in this case, like a magnetic field is about like a 5 micro Gauss. Okay. So inspired by this result, we just pursued more X-ray observation from the Swift telescope for 3 more lossy sources with no known like low energy counterpart. And for all these 3 sources, it's like nothing. So upper limit only. So there is something, seems to be something there, but it's not a real relevant source. But again, this upper limit could be useful eventually when we maybe study broadband signature, if any low energy counterpart can be detected in other wavelengths. So this work is led by a group of students at MSU. So again, like if we really want to confirm and convince the community, like a specific class of galactic sources can be like hadronic sources, we do need like the signature and the neutrino signals, right? So there have been just lots of effort within the S-Cube collaboration on doing population studies, stacking like all the nebula, maybe stacking all the supernova remnants with cloud interaction and search for their neutrino signal. So what my group is doing right now is to examine another type of PeVatron candidates, which are the star-forming regions. So there has been some papers in recent years pointing to massive stars, right? And their wind could be like a cosmic ray, could accelerate cosmic ray protons. So what we are doing is that we just choose a sample of the young stellar, massive stellar clusters, star-forming regions in the northern sky that is optimized for S-Cube to analyze, and we want to stack them up to try to find their neutrino signals. And the feasibility study looks promising, especially the Cygnus X region could have a very high potential, but the stack of them could be also slightly above detection threshold of S-Cube. So our group is leading the analysis for a star-forming region in the northern sky, and the Kavli and a Harvard group is looking at the star-forming regions in the southern sky. So more news will come from for this class of sources. So here's my summary, just some good pictures. The filaments in the galactic center, some of them might be connected to the galactic center PeVatron, and there are very active ongoing efforts to identify PeVatrons outside of the galactic center as well. Thank you.
Right, thanks, Shuo. We have plenty of time for questions. Chris?
So do I infer from your last slide that constraints on the gas environment of PeVatron sources, except for the galactic center, it's still largely an open question?
The gas?
Well, how dense, if you had a PWM in a very dense environment, perhaps that will change the shock acceleration process. So it's been suggested, right?
Oh, I think in our current modeling, we're still just in a very early stage. Like maybe just try to test like a hadronic versus leptonic. The model parameters, I think we maybe cannot really probe like the surrounding density.
Well, others here could say more about the potential for the strength of the ambient magnetic field to be a relevant parameter.
So the magnetic field within the system is we consider as a free parameter in the model. Yeah.
Thank you.
But ambient density is
Or field.
is within the model.
Oh, cool. Hello. Sorry if I missed this, but when you were talking about the radio filaments and you said polarization was detected, can you just, do you have like a number for polarization degree? Because I can imagine if it's, you know, one flux tube, that it's pretty ordered and would have a very high polarization degree.
Indeed, I'm not familiar with the radio polarization detection. That's what I only see from the literature. I do not have that polarization degree in my mind.
Okay. And so you said X-ray polarization. Are you like submitting to XP or something? Or?
Oh, XP cannot really resolve these filaments. Okay. Yeah, they are too faint and too small. I think Zhang mentioned like the next generation of X-ray polarization telescope, EXTP. I don't know whether EXTP, for example, would be able to resolve, but it sounds like not. These are very faint and small scale features.
Lorenzo?
It's a little bit of a broad question / comment. So a lot of these filaments, as you mentioned, and other filaments like X-ray, so like jets or X-ray filaments that are coming out of Bauschock nebulae, they're always puzzling in the sense that there is no, in some cases, there is no obvious dependence, spatial dependence of the emissivity or the spectrum. There seems to be that these particles are just ballistically going, and then at some point they stop. I don't know if you have like thought about some underlying reason for why we don't see spectral variations along the filament, let's say, or in which cases we do, in which cases we don't. Anything related to that?
We do see spectral variation along the filament. Like for example, for this case, it's not like doable for all the filaments. We can only do spatial resolve the spectra for bright enough filaments. But for example, for this filament, I don't have the figure here, but it's in the paper, we do see spectral softening as we go further away from this source.
But I have in mind, for example, the X-ray jet of the guitar nebula, right? In that case, I think there's nothing seen, right?
Could be, but when we, for example, study this one, we are thinking about the guitar Ptolemaic nebula as a comparison. We think that for this case, it could be just like the jets from the the Ptolemaic nebula. So not necessarily all the filaments can be explained by some global model. Like it could be jets. I think there are Barkov's group. They published a series of paper. Oh, okay, good to know. So it explained like the X-ray filaments using the jet from Ptolemaic nebula.
How many of them actually are associated with PWM?
That we don't know. I think I would leaning towards if a filament has a point source in the middle, I would think it would be more likely associated with PWM jets. But like in other cases, if there's a point source that should be detectable, like for example in this filament, there's no any embedded points, obvious point sources. So that seems to need injection of electrons from outside of the system. But this is a question I think we want to maybe more carefully examine, especially we have new filament samples there.
Thanks for the nice talk. In the Meerkat maps, some of the filaments of the galactic centers are like little harps. They've got multiple periodic strands. Are some of those the same sources you're talking about, or are those different?
So you mean these like a Meerkat radio filaments?
Yeah.
So among like the about 25 known like reported X-ray filaments, 5 of them have radio counterparts. So still a small number. Just about 20% X-ray filaments has radio counterparts. So like the case like this is very rare.
Okay.
Yeah. With both X-ray and the radio. Yeah. But however, we are just trying to redo this right now. I think that the number for filaments with both X-ray and the radio would definitely increase.
Sure. Yeah. We can talk offline.
Do you observe like any Kevin Helmholtz instabilities on the sides with your observations?
That's not something we can, I think, directly.
Okay, because I read somewhere that sometimes they should be unstable to it, but they're not, which is a bit weird.
They are very, very stable source. Yeah, observationally, we're only trying to see whether there is any like a variation, right? In for example, spectral index and in luminosity. Like in X-ray, we can compare. We can consider the horizon of like 25 years. Radio is like the horizon is like about 50 years. No any report on variation on both luminosity and also spectral index for any of these filaments. Very stable. And the puzzling. So I just want to mention that whenever I give this talk to astronomer community, the most often questions I receive is like, how are they formed and why are they so stable? I like this would be down to a plasma physicist also.
Thank you. I find it strange that this talk was aimed at galactic PeVatrons, and yet all of the questions asked are not about galactic PeVatrons, but about these filaments. And I will also ask a question about the filaments.
Sure.
With apologies. Are there any hopes to see them in any other wave bands other than radio and X-rays?
They are not really observed in other wavelengths.
Okay. So we just limited to this.
Yeah, so far they have only been reported, detected in X-ray and radio.
Thank you. Maybe somebody could ask a question about something else.
No worries. I felt like the filaments could interest this community better.
When you talk about the galactic center as a possible PeVatron, are you really thinking like vicinity of the accreting black hole, or are you thinking some other objects? That, there's lots of garbage out there.
My personal preference is it is the galactic center supermassive black hole. It is such a star. So it's very inactive and quiescent right now, but it used to be a lot more active, even just a few hundred years ago. So it's likely that they maybe used to be more efficient in proton, in particle acceleration in general. But the detailed mechanism is, of course, unknown.
So some sort of past jet activity that you envision?
Some past outbursts due to unknown reason, because we see some observation evidence for molecular clouds that was lit up that points to a very active past activity for such a star a few hundred years ago. Yeah.
All right, any other questions? All right, let's thank Shuo again then. And